Hello, everyone. I am going to do my best to make this recording from my iPad. And believe it or not, I actually feel more nervous about doing this than getting up in front of the class. But that's okay. We're going to make it work. I'm not going to record my face because of the weird angle that the iPad would be sitting on the desk. So, first point, which you already hopefully all know, is that in-person class is canceled today. We are going to not penalize anyone for wanting to go and express their constitutional rights. So, I hope that many of you are at the protest today. And this is one source that I found online about the Ice Out rally. My guess is that if you just drive downtown and try to find a parking spot, you will be able to figure out where there's going to be a protest because I hope that this is a very large event. But I also have left a post on Ed Discussion, and I would recommend that you go there if you're looking for other people to drive with and attend the protest with because it's more powerful when you do it with other people. So I hope to see many of you there. I will definitely be going myself. So our class plan for today is that you can watch this recording and then complete the worksheet on your own time. This is going to be due to grade scope, so there's an assignment that is posted already. It's called A8 linear partition, and if you want to be able to find that PDF, this is a general lesson for where I store the PDFs, but you can go to the Canvas page. Go to Files on the left-hand menu, navigate to Worksheets, Week 3, and then the one for today is A8 Linear Partition. In general, that's always where the worksheets are going to be located. And I've had a number of questions from folks before or after class about this. I try to batch them out and post them all on Sundays before class, so they're always available to you. The other thing I will point out is that the slides are always available pre-class. And then after class, I post the annotated slides, usually within about a day or so of class being completed. And those are in the files, slides, and then navigate to the correct week directory. So these resources are always available to you, but in order to be able to do the assignment today, you'll have to go download that PDF from the A8 from week 3. So that's where to find it for today. And the instructions are that you need to upload that anytime before Sunday at midnight, so there won't be any overlap with homework 2. And yeah, this should hopefully take maybe even a little bit less time than an hour, since usually class periods are 50 minutes. So we'll do our best to be efficient. So today we're going to be doing a problem, working on a problem called linear partition, and you might find it a strange problem, but it's actually something that you could think about as being motivated by a real world problem. So first of all, did you know that you get free newspaper subscriptions through Minds? I didn't know that for actually a couple years of working here, and then one of the professors told me, and I was like, my mind is blown. So you can go to a whole bunch of different newspaper sites and create an account with your Minds email. The instructions are located here, libguides.minds.edu, news articles. For example, there was an article just a couple of days ago about Anthropic and about how they have this massive warehouse of books. And they are going to do what is called destructive scanning, which means that those books get destroyed in the process of scanning them in. And then they use it to train AI. So this is kind of one of those hot topic of the century right now, IP issues and copyright issues with books. And it is hotly debated and hotly contested, but it seems like the general legal consensus is that as long as the books were acquired legally, then it's okay for AI to be trained on that. My question for you guys, do you actually think that that's an ethical thing to do in the first place? I don't necessarily have a one correct answer to that, but the legality of it seems to be that as long as you acquired the book legally, then you can do whatever you want with it. They were recently hit with a huge lawsuit and a big fine because they were pirating books and using the pirated books to train. So that's clearly illegal. But I also had another conversation literally earlier today with a potential collaborator who works at a large archive of materials and we were telling me all about they actually do this. They purchase books legally and scan the books, and then they make them accessible for universities or other types of training places like seminaries. So this is actually a real problem. And the problem that we're going to try to solve here is this job of scanning books, right? So we are going to define the terms that we have a shelf of books, we have K workers, and we want to leave the books in the sequence that they already are located on the shelves. We don't want to take them out into big piles or something like that because that just creates a lot of extra work. And when we're dealing with this much raw material, it's actually a substantial task. Think about making piles of millions of books. So what we want to do is we want to divide the shelf into K regions and assign each region to one worker. So what they're going to do is they're going to go through the books in that region and they're going to scan them in. So let's think about a couple of examples here. I guess before we get there, though, last thing I'll say about this, um, the key question motivating this is what is the fairest way? So I will write this down. What is the fairest way to divide up the shelf? And by fair, I mean we want to make sure that each worker is scanning approximately the same number of pages, but obviously books come in many different pages. So this is easy to think about if we knew that all of the books were the same length. Say they were all 100 pages, and this is we've got 9 books in this first example here. So with 9 books and 300 pages each, that's easy, right? Averaging works just fine. Averaging works just fine if all books have the same length. Or I'll say same number of pages to be a little bit more precise about that, right? But what if the books are not the same length, right? If we were to take that same strategy, so I take the first 3 books, the second 3 books, and then the last 3 books, well, then the number of pages here would be 600 pages. This one would be 1,500 pages, and this would be 2,500 pages. So clearly, I can't just divide the shelves by some average number and take it. I have to think more carefully about what number of pages is appropriate, right? And it turns out that if we think about that problem, let's rewrite our list here. So we've got books that are 100, 200 pages, 300, 400, 500. Well, how convenient that we have nice increasing numbers here. Makes it a little bit easier to reason about this. Um, if we wanted to do this a little bit more fairly, then our divisions would need to look something like this, right? In this case, the sum of 900 and 800 is 1,700. And I'm probably going to make stupid math errors. Hopefully not. We'll see. 700 and 600 is 1,300. And then the rest of these, so this is 900, 1,200, 1,400, 1,500. Okay, so that's a whole lot closer to fair, right? It's not perfect, but it doesn't have to be perfect. We're just going to do the best that we can with the numbers that we're working with, right? Um, so hold on. Yeah, okay, great. So here is the formal statement of the problem, right? We have the input, which is a given arrangement S of non-negative numbers, S1 through Sn, and some integer k. What are these S's? These are all the number of pages per book. And as with all of our other DP problems, this is left to right ordered, right? They're in a sequence. What is the sequence? The sequence happens to be the order that these books are arranged on the shelf, right? It correlates to some real property of the real world, and we have to work around that real world property, right? Because we can't just make stacks of books very easily otherwise. So the problem is that we want to partition S, this arrangement S, into K ranges so as to minimize the maximum sum over all of the ranges. So think about that for a second. There's minimizing, right? We're looking for the smallest number, but the numbers that we're looking at are all sums, right? They're sums of the number of pages within a given range. So we're trying to minimize, get the smallest possible maximum across all of the ranges that are available to us. Okay, so stick with me here. This one gets a little bit complicated. I think this is a good thought exercise, right? Because it really lets us explore. Um, I've told you before in class, right? Usually a DP problem is involving a minimum or a maximum. This is actually involving both, right? Mind equals blown. We have to consider lots of different kinds of problems, and this one really kind of stretches it to the limit. Okay, so let's try to build an intuition for how we might do this, right? Consider the input 100, 200, 300, 400, 500, 600, 700, and we're trying to go for 3 partitions. The question here is, what is M of 7 comma 3, right? What does that mean? The 7 here is referring to what? The number of books that we have, or N. We have N books. 3 is the number of what? Partitions that we are going to make, right? And that in this problem is going to be K. Okay? So let's draw this out. We've got 100, 200, 300, 400, 500, 600, 700. So the reason that this is possible to figure out just by visual inspection is because it's a very small set of numbers and you can kind of mess around with it a little bit. It turns out that if we tried out a couple different combinations of things, we want to kind of lump together some of the bigger numbers because we're trying to minimize the maximum. It turns out that 700 is going to be in one set all by itself because it's a large number. And then the next partition will go right there, right? So this number is going to be 1100. The sum of those 2 books right there in the 5th and 6th position is 1100. The sum of the last position is 700 because it's just one book by itself. And then the sum of the rest of these guys is 100 plus 200 plus 300 plus 400. And it turns out that that equals 1000. So what does this return? Right? We want to return the minimum or the okay, hold on. Let's go back here, right? Minimize the maximum, right? We want to take the smallest maximum possible, right? Well, that turns out to be 1100. Okay? 1100 gets returned by this. So, if we try to come up with a formula for this, how might we do that, right? What we're going to try to do here is think about what's an intuition with DP in general is that we're going to try to make the problem smaller by 1. Okay, and there's kind of 2 different options or 2 different ways of thinking about that. One way to think about making this problem smaller by 1 is to think about changing this number here, the 7, right? Make that into a 6. The other way to do that, or to think about this, is to think about changing this number here, the 3, and going down by 1 smaller size. And it turns out that in this case, the correct intuition is actually to think about the 3 instead. Let's try going down by one fewer partition, right? What does this problem look like if I have one fewer partition? Okay, so let's think about that on this next slide here. So I'm going to redraw my list of numbers just to kind of make this easy to visualize and demonstrate what's going on here. So we have 100, 200, 300, 400, 500, 600, 700. And we're trying to minimize the maximum amount of work. So let's think about what happens if I think about making my number of partitions smaller by 1. Instead of 3, I'm going to look at 2 partitions. And I'm going to iterate through all the different possible sizes of the problem. So 1 through 7. If I have 7 books, I'm going to think about what happens when I look through this problem at every different size at this level of the problem. So let's start off with this first one here, M1, comma 2. Well, what does that mean? That means I'm only looking at the first book and saying, okay, well, what if I have 2 different partitions? Well, when I only have one item, that means that the number of partitions is kind of arbitrary, right? I could put any number that I wanted in that second position, and the maximum amount of work is always going to just be 100. It's going to be whatever the number of pages is of that one item, right? So this is actually this is going to turn out to be one of our base cases, right? 1 comma really any k, because I don't know why that happened. But the price here, or the cost here, the number of pages is 100, because if I'm trying to make 2 partitions and I have only access to this one first item here, then it's going to have to be whatever the number of pages is of that item. So for this next row, put that, my 100 went away. Now I'm going to be thinking about the first 2 items, and I have to partition that into 2 things. So, okay, there's only one choice here, 100 and 200. I have to put the partition between the 2 of them. And the maximum amount of work in that case is 200. I don't have a choice again there. So that's pretty clear. What happens? Got to keep on redrawing my zeros here because my eraser is too big. What happens when I think about the first 3 items? Now I actually have some choices, right? I have to add one partition in here. And my choices are either that I put my partition right there, in which case I have a cost of 100 in that set and a cost of 500 in that set. But that's clearly not going to be optimal, right? So let's not consider putting the partition there. Instead, let's consider putting the partition right there, in which case I have one option of 300 and another option of 300 on that side. And so clearly, this one is the minimal maximal, or the minimal max amount of work, and my answer is 300. Okay. Now, what happens if I think about this region of the problem, right? I've got the first 4 books. Things start getting a little bit more interesting at this point, right? Because I have 2 places. I have to put a partition somewhere. And so my options are to put it right there, in which case I could say I've got 400 on that side. And then, well, now this looks like it may or may not be optimal, right? I've got 400 on that side, and then I've got 600 on this side. That's my first possibility for making 2 regions in this problem. The other option would be to do what? To put it right here, in which case I've got 700 and 300. But this is not as good as my last solution because my last solution had 600. The last possible choice that I have would be to put my partition right there, and then it just got even worse. Now it's 900 and 1,000, or not 900 and 100, right? So that's the worst possible choice that I could make, right? So it turns out that for this particular one, I get the best situation if I put my partition right there before the 400, and then I sum those 3, and I get a total of 600, right? The minimum maximum is 600 in this case if I put my partition right over here. Okay. So erase all these ones that I'm done looking at. Great. Moving on to the next region of the graph. We're looking at the first five items here. And just for the sake of time, I will save us a little bit. That turns out that putting the partition between the 300 and the 400 is the correct solution. We get 900 and we get 600 over here. If you put it anywhere else, the costs just get worse than that. Okay. Next section of the graph is going to be all the first six items. We have to have two partitions. It turns out that the best way to do this, let's see here, um, we have to do two partitions, and if we do it right there, then we get a cost of 1100, and this cost on the left side of this is 700 plus 200 is 900 plus another 100 is 1000, right? Those are pretty close, pretty equal, close to equal to each other. But this is the minimal maximal, because if I moved it anywhere else, that number would just get higher, right? This is going to be 1100. I guess I'll just demo that for fun, right? What if I had put it here instead? Well, then the price over here would have been 600 plus 500 plus 400, which would have been 1500. And then on this side, it would have been 600, right? So then my maximum actually is higher. 1500 is higher than 1100, right? So that's not the correct answer, right? This partition right here makes more sense and gives me a cheaper a more minimal maximum. Okay, we're getting close. Okay, and so then finally we have M7 comma 2, which considers the full length of the whole array, and it turns out that here we're going to end up with if I make my partition right here, I get 1300 on this side, and then 900 plus 300 is 1200, 1400, 1500, 1500 on this side. So this is the best way to do it. It turns out in this case, you can play around with the other options if you want to convince yourself of this, but this is going to return the minimal maximum of 1500. Okay. So try to convince yourself that those are the correct solutions and play around with it. So now what I'm going to do is I'm going to try to write a recurrence relation, right? I want to write a formula for 7-3 in terms of the problem when it's one partition less, in terms of when we only have k equals 2 partitions available to us. Okay, so a hint for thinking about this is that we will notice that the kth partition starts right after we place the k minus 1th partition. Where can we place that last divider? Think about that for a second. Where can that last divider go? The answer to that question is anywhere between the ith and the I plus 1 book for some value of I. So then what's the cost of that? Right? What we're basically doing is we're thinking about how do we move around where our I is at any level of this problem based on any number of partitions below K, right? And we're going to think about this problem by moving that I around and then selecting the minimum max based on moving the I around. Okay, so think about that for a second. This is kind of a tricky one to think through, but it's really rewarding when you kind of figure out why that works in your head. And we can always talk about this at office hours if you need to have more clarification about this. So, coming up with the formula now. We're going to combine our mins and our max into a nice equation, right? And this is not the general formula. This is only the formula for M7, comma 3, right? M of 7, comma 3 is going to be equal to the minimum if I move my I around from I to 7, right? I'm thinking about any one of those indices at those different places, right? The minimum of the max of mi comma 2, which is all of these terms that we just calculated. That should be another bracket right there. And the cost of the last partition. So we'll start with j equals I plus 1. Everything past where I currently am up to n of the number of pages of that jth section. Okay. So if I was going to try to describe what these terms are in English, right? This is the cost of the last partition. And this is the minimum max of the first two partitions. Okay. So we have to think through going through all of these values up here that we already just calculated and what's taking the minimal max of all those things. And the total cost is going to be the larger of those two quantities, either the cost of the final partition, right? That's this term as we defined it before, j equals I plus 1 to n with the number of pages in each one of those sections, or it's going to be the cost of the largest partition formed to the left of I. So what we need to do is we need to partition the elements S1, sorry, that's not an SI, that should be an S1. Partition the elements from S1 dot 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 all the way up to SI as equitably as possible among K minus 1 ranges. So this is just a smaller instance of the same problem, right? Now we just have a new linear partition problem. It's a smaller instance of exactly the same problem that you were thinking about previously. And we can just recurse down, right? And keep recursing down through that smaller problem until we finally hit a base case, right? So once we fix that last cut after some position j, right, whatever remains on the left, splitting S1 through split Sj into k minus 1 contiguous parts to minimize the largest block sum is the same type of problem, just a smaller instance of it. Okay, so what's the general case of this? We were working on this for M3, 7, or M7. We were working on this for M7, 3 previously, but how do we express this in a general way? Pause the video right now and see if you can figure that out for yourself, right? This is a good thought exercise. Of course, I'm not in the room to enforce the pause, so I will go ahead and write it down right now. But I hope that you give it a little bit of thought on your own before I just tell you, right? M of n comma k in general is equal from the min from 1 to n. And similar to before, we're going to take the max of two things. My same problem, right? But I'm going to take one fewer partition, right? And then we've got the sum term that looks at everything that's to the right of that. J equals I plus 1 all the way up to n of Sj, right? The number of pages in the books to the right. So that's the general recurrence that we're talking about here. It should work with any values of 7 and k, but what's the last thing that I haven't given you yet, right? I haven't given you the base cases, although I kind of talked about it for a second a little bit earlier. The base cases look something like this, right? I take M1 comma k, right? This is that situation. I'm only looking at one book. And so it doesn't matter how many partitions there are. It doesn't matter how many sections there are. It's always going to be equal to what? The number of pages in that one book. So S of 1. Whatever the number of pages are in that one book, it's going to be equal to that book. And it is the first book, right? The other base case is if I'm at J, I'm at some arbitrary index J, but I'm only looking for one section, one partition, right? Well, what's that going to be? Sigma from I equals 1 to J of the cost of the pages at that index. If I were to draw that one out, let me draw an example of this, right? 100, 200, 300, right? If I'm saying that I want to, let's say that J equals 2 for this base case, and I'm trying to find out M of 2, comma 1. That means that I have these two books that are up for consideration, but I'm only trying to form one possible grouping of them. I'm not trying to split it into anything else, right? Well, then I need to take the sum of both of those two things. I have to take the sum from 1 all the way up until J in order to get that total, right? So those are my two base cases. And what this looks like, if you were trying to figure out what the recursion tree looks like, that's actually kind of a complicated problem, right? Because you end up having lots and lots and lots of computations per each potential maximum cost calculation here. Okay, so let's think a little bit about what the runtime is going to look like for this, right? We have k partitions that are going to need to happen, and we have n values across that list of S, right? So the cost here is going to be the number of cells in the table times the runtime per cell. Think about that for a second, right? In each cell, we have to calculate all of these different possible maxes that could happen there, right? So there's a lot of um, repetitive possible calculations that are going on here, right? So they're going to be k times n cells in some DP table, right? Each cell depends on n others and other cells and can be computed in linear time. So what this ends up happening is we have an O of k times n, because that's the size of the table that we're working with, but that gets multiplied by an O of n time, because completing all of those n maxes means that we're going to have to do that in linear time, right? Each time that we make a calculation. So the overall runtime here ends up being O of k times n squared. Okay. So this is a tricky problem to think about, and you might need to kind of logic your way through it a little bit, a couple times. And if you're struggling with this to make sense of it, you can always come chat about it in office hours, and I'm happy to give this more time. But that's the last DP problem that we're going to be covering this for this unit of the class. And just a quick reminder, right? When can you use DP? DP computes recurrences efficiently by storing partial results. So it can only be efficient when there aren't too many partial results to compute, right? So you have to think about, if I was to try to solve this problem recursively using a classical recursion tree, right? Am I able to avoid recomputing things if I come up with a DP solution that lets me skip doing those recomputations, right? I have to show that the number of computations in my DP solution is less than what the number of computations would be. I'll write this down, right? So the number of computations in my DP solution must be less than the number of computations in the purely recursive solution. And it usually works best on objects that are linearly ordered and cannot be arranged, right? So characters in a string was one example that we talked about. We talked about this row of books example, right? You can't just make them into piles on the floor. That's actually labor intensive. And so the real world ordering of these books on the shelves matters, right? So when you're doing your grading, what you're not your grading interviews, if you're interviewing for a job and all of a sudden they're mentioning that something has to be ordered in a left to right way, it's pretty, it might be the case that that might be a DP problem, and that's a good strategy to kind of think about. Okay. So office hours are live. Of course, my office hours are canceled for Friday. I will write that down just to confirm it, right? So Professor Smith's OH are canceled because I will be at the protest. I hope to see many of you there. Homework 2 is due on Saturday night, and DP Project Part 3 is going to be due next Wednesday. If you'd like to provide any feedback for this week, please go ahead and do so, especially if you have any feedback about how I'm managing this asynchronous class session. I'd be happy to hear it, because it might be relevant again later on in the semester. So thank you so much, and I hope that you guys have a great weekend. And I'm going to go ahead and try to figure out how to stop recording.